Ladies and gentlemen, hi. I am Soulimane KAMNI, PhD student within the LIAS laboratory, which is located in the ENSMA Engineering School in Aeronautics, located in Poitiers, France. The real-time group of my lab focuses on modeling and analyzing critical real-time embedded systems. Indeed, these systems are widely used in fields like avionics, automotive, nuclear power plants, and so on. The particularity of these systems is that they must be safe and correct, because if any failure occurs, then that may imply disastrous consequences. So in order to ensure their correction and safety, these systems are intended to be correctly designed. In most design methods for real-time embedded systems, like for example Arcadia, the model-driven engineering standardized by the OMG, recommendations of the AutoSAR standard, and even old methods like the ones based on structured analysis, the system architect is facing at some point a set of interacting functions. If life was ideal, these functions could be continuously executed instantaneously and the design job would be finished. Nevertheless, of course, each function requires computation, therefore has a nominal duration. As a result, the system architect, having an idea or not of the target hardware architecture, must choose how often the functions should be executed. In computer science, given an activation pattern to a function or a set of functions is affecting them to a thread. In this presentation, we call this process deployment of functions into threads and of threads onto hardware resources. This is not an easy task and has a high risk for the system's correctness, as deploying threads on shared processing resources and shared communication media implies the necessity to arbitrate the resources, using, for example, a scheduler. And a bad design, by bad here I mean threads that won't be able to meet their deadlines. So a bad design detected late in the life cycle of the software is going to cost a high price. The later the detection of the problem, the higher the price to pay. Despite its old and respectable age, the V-life cycle and its variants is still suited and used for critical real-time embedded systems. Usually, in this life cycle, the deployment takes place somewhere between the specification and the preliminary design. The problem is that the system architect in charge of this phase will know only at the validation phase if his system can meet the performance requirements. The delay between design and validation can be as long as 6 to 8 months for a Space Pro program to 6 to 10 years for a new airplane. Of course, in order to reduce the risk, one can over-provision for computing resources, increasing costs and reducing energetic autonomy. Our goal is to automate the deployment process, given some information on functions durations or assigned time budgets. Actually, several deployment methods exist in the literature. Each method solves a very specific problem based on a very specific assumptions. We call a set of assumptions a context. By the context, we mean the kind of the threads. Are they independent? Do they communicate? Do they share resources, etc.? The composition of the physical architecture, the hardware used, and so on. Moreover, constraints that should be expressible by the system architect are not only based on timing constraint, but also on domain constraints. For example, few methods propose to express the need for redundancy of some functions or segregation, intellectual property, reuse, etc. As a result, several automated deployment methods proposed in the literature are too ad hoc to be used in the industrial context. Nevertheless, system architects face a complex and confusing design task. Hence, it is delegated only to the most experienced designers. Our objectives are as follows. We want to help the system designers deploy their systems even without deep knowledge in the optimization, and how this can be done. First, we want to help the system architect to express the inputs of the deployment process. The inputs represent the functional model and the physical execution model in addition to the set of the constraints that must be respected, including the architect constraints, domain constraints, schedulability constraints, performance, etc. Then, we want to capitalize the efforts by gathering the existing deployment methods in a repository and allow to share and update them. The deployment process requires a real-time system as on input defined by the functional model F that consists of functions, their activation patterns, their time budgets, and their precedence relationships. H, the hardware model that consists of a set of execution processors, their core kinds, single or multi-core, their provider or frequency kind, homogeneous, uniform, or heterogeneous cores, and a set of network buses, their topology, their bandwidth, and their protocols, like CAN, IFDX, AVB, etc. The set of the constraints, C, that should be respected. Among these constraints, we can find scheduling related ones like end-to-end delays and business ones. For instance, for safety reasons, two functions should be segregated. The behavior of the functional part may be represented as directed acyclic graph where vertices correspond to the system function set and edges correspond to the interaction set between functions. The exact description of the system is indeed required as input in order to know what kind of schedulability analysis can be done in this particular context. The mapping of functions to threads is corresponding to assigning a rhythm to the execution of the functions. The mapping of threads to cores and messages to networks is implying a resource arbitration which is provided by schedulers for computing resources and arbitration for networks. The result is what we call the operational model. It is the first result of the deployment process. This operational model has to meet the constraints of the constraint set, which includes timing constraints. These timing constraints can either be individual, applied directly on a function, or be expressed on functional chains, requiring several response times and transversal times to be computed. The proposed framework will be composed of several components. The first component is a repository that stores the optimization methods. It should group all the existing optimization methods that exist in the literature and should be extensible for future works. The second component is the front-end side of the framework, dedicated to system architects, which would present a graphical mechanism in form of a domain-specific language used to express the functional model, the scheduling constraints, business domain constraints, and the performance constraints. The functional specification would have to be conformed to a real-time modeling language such as UML-MARTI, Time4Sys, or Mozart. Likewise, for the design requirements, they would have been expressed to conform to a requirement modeling language. To ensure the automation of the optimization process, the framework would contain another component called context detection process. This mechanism should automatically guide the architect to the right optimization methods. The context concerns the set of information provided on the hardware, thread scheduling policy, the functions model, the metrics to optimize. The analysis tools already exist. However, a connection to these tools is necessary since all the modules must be communicating to ensure the automation of the whole process. The framework would be connected to use in a systematic way schedulability analysis tools thanks to helpers tools like Mozart framework, which allows to find the appropriate scheduling test and get eventually the suitable model. The optimization process will operate through two steps. The first step is dedicated to finding a design space of candidate solutions that meet constraints. So, as input of the first step, we will give a real-time system. The set of constraints allows us to propose the mapping methods. The framework should propose an order relationship between constraints. Hence, when no solution exists, relaxing some constraints should be possible. Also, the set of constraints allows us to define an objective function. The goal of the objective function is to minimize or to maximize metrics. Yet, the objective function has to call the appropriate schedulability test to check the schedulability of a candidate solution. In order to exploit the mapping methods, a transformation toward the optimization formalism such as MILP, SAT, heuristic-based or meta-heuristic-based formalism should be proposed by the framework. The second step is dedicated to prune the design space. The pruning is driven by the metrics to optimize, such as the minimization of the end-to-end latencies, the minimization of the number of context switches, the maximization of the slack, etc. Then, regarding the number of metrics to satisfy, the design space will be reduced. Finally, the output of this step could be favorable so that one or more solutions are given. Otherwise, no solution could be possible. In the latter case, constraint relaxation suggestions should be proposed to the system architects so that the new system would accept at least one solution. Thank you for your attention. You can address your questions directly to the authors by email.